So welcome all to week 4 tutorial. This is week 4, not week 3. Week 4 tutorial for the course Deep Learning. I'm Pintu Kumar. I'm a PhD scholar at IU or IIT Bombay. So today the topics that I intend to cover are some variants of gradient descent method. So I would cover momentum based method, autograd, Adam optimizer, right? So I'll cover some basic details and questions related to it. And at any time during the conversation or the tutorial, if you have any doubt, you can either type it in the chat box, I'm monitoring it, or you can unmute yourself and speak, right? So you can clarify your doubt. In the last session, somebody asked about some good book or resources. So I pointed out to a book by Ian Goodfellow and Yusha Benjo. That is a very good book. There is one more resource. So this book is called Dive into Deep Learning. This is actually not a book, but more than book. So it's a book written by some researchers at Amazon. So they have a dedicated website for this book. This book is in form of a website. The website is d2l.ai. So if you go to that web page, you will find something like this. So on the left hand, you have all the topics that they are covering. And for every topic, first they have explained that topic, not in that much depth, but they have explained it to sufficient depth. And then you have codes available for them. And that too, the codes are in 4 different libraries. So you have PyTorch implementation of that, TensorFlow implementation of that, JAX implementation of that. So you can actually sort of look at a topic. For example, this page is implementation of multilayer perceptron from scratch. So there is everything included over here on this page. I can probably show you one of the page that would be more helpful. And also towards the bottom, there is a discussion forum where people post their questions and many people reply to them. So this is sort of an active page where people are taking advantage of it. I'll probably share this particular page and show it to you guys. That should be more useful to you. So last time somebody asked, I think last time I didn't remember the name of this book, but yeah, I also found this resource pretty useful. So you can benefit out of it. So this is the page that I was talking about. This is D2L. This one is not I but L dot AI. So there is a linear neural network for regression for classification. Then there is this multi-layer perceptron that we have been talking about. Implementation of multi-layer perceptron, then forward pass and backward pass computation. Okay, then there is something about dropouts. Then they have gone to convolutional neural network that will cover in future. So they have a variety of topics that we would cover, and there are many topics that we won't even cover in this course, but are useful, right? So for example, if you go to forward and backward pass computation, and so this computational graph, so they have explanation over here, what is backprop and everything, right? There are some exercises given, and again there is a discussion going on at the bottom where people help each other understand topic better. So this is, we started from 2020, people have even posted in August 23. Okay, and so like if you guys can join, you can help each other. So this is implementation where this is implementation of multi-layer perceptron from scratch. So you have a PyTorch implementation, right? So everything is given step by step. So here they are constructing a class that they'll use. So they are defining this weights and biases over here, right? Then they are defining the activation layer over here. This is the forward pass that they have defined. This is how they'll train their set and how like the kind of data they have. Okay. So this is a concise implementation that they have. This is purely based on PyTorch. The earlier one was slightly from scratch, but this is a very concise implementation that they have. Okay, so yeah, so you can try visiting this page. It might be useful. So this was in PyTorch library. Then they have TensorFlow implementation also if somebody is interested in TensorFlow. I generally prefer PyTorch, but if somebody is interested, the person can visit. Okay. So this was regarding what somebody asked in last class. So I'll continue with today's topic. Yeah. Okay. So so we'll begin with today's topic, and we'll begin with something. Okay, so we can have a small recap first, then we'll go to contour maps. Okay. So if you remember, what do we have? A multiplayer. So I'll start with a very small recap. So we have a multi-layer perceptron, and a multi-layer perceptron looks something like this. So every connection has some weights associated with them. Okay, and our goal is to learn those weights. Okay, so let's say this is the vector containing all the weights is called W. Then our task is to learn W. So how do we learn? We define some loss and we try to minimize that loss. The approach that we have discussed to minimize that loss is something known as gradient descent method. Okay. So what does gradient descent method does? So let's say you initialize some W node randomly, most probably. Then you will take W1 to be W node minus some eta times gradient of loss function with respect to W. This is the approach that we take, right? For the second step, you will have W2 is equal to W1 minus eta times grad of loss function with respect to L. This is what we have done till now. So there are some disadvantages associated with the vanilla. So this normal gradient descent is called vanilla gradient descent. Okay, so there are some disadvantages associated with them that we'll talk about, and we'll see how we can uh, propose a method that overcomes those disadvantages. So let's begin with something that is known as contour maps. So many times, sort of visualizing 3D plots are not very easy. So what people have tried is, so they have tried to project this 3D maps onto a two-dimensional plane. Okay, where we can do our computations easily. So let's say if this is your 3D map that we have, so this image one, first image that you have, this is your 3D map. So first step that you're going to do is, so this is your x-axis, let's say, this is your y-axis, and this is your z-axis. So z is a function of x and y. This is something like this. Okay. So your function value is plotted along the z-axis. Okay. So what you will do is, you will draw planes parallel to xy planes. Okay. So what you're doing is, you're cutting your figure at some height. So height is represented by z. So you are cutting your planes at some particular height. So if you look at this figure 2, so this I have taken from Khan Academy's page. So what people have done is, these people have done is, they have taken these four, this one, two, three, four different heights, and they have cut the 3D plot at these particular heights. Okay. Then what they will do is, they will draw the exact points where these planes have cut this plot. So one is this, then this is for the first one. For the second one, it has cut it at this place. Okay. So they have plotted it something like this. Okay. Then they'll forget about the 3D plot they have. So now whatever they have obtained, that is their representation for the 3D plot. And they'll forget about whatever we had earlier, and we'll just be left with this thing. Okay. Now we have some height associated with every curve that we are drawing. But what we will do is, we will project everything onto a 2D plane. Okay. So this is the 2D plane that we obtain. So this is something that is known as the contour plot for your figure. Okay. So we sliced your plot at different heights. We obtained the curve where it is crossing that particular function, and then we have pressed it onto a 2D plane, and we have obtained something like this. So you can see that there were two circles that are being mapped here. Then there was a infinity kind of a sign that is being mapped here, and so on. Okay. Okay. So one question that is sort of there in assignments is like, what does the gap between these contour mean? So for example, this 2 over here means that you have cut your plane where f value is 2. So f of xy was 2, and you have cut your graph over here, and you have cut your graph at f of xy is equal to 1. One thing is this. Second thing is, if you look, this gap over here is lesser than this gap over here. Okay. So the function values are same, but over here the gap is less, over here the gap is more. So when you have less gap, right, that means in less amount of time you have traveled from function value 2 to function value 1. That means the slope of that curve is steep over there. Okay. So if you have less gap, that means it is the function is more steep over there, steep in that direction. Okay. So if we look at this curve, so this is the point sort of from where we are starting. If you look at this direction, okay, black is very bad choice. If you look at this direction, and if you look at this second direction, you can clearly see that this pink one is more drastically falling. So that's why we see in the contour that the gap over here is less, okay, or over here is less. So less gap means the function is more steep over there. Okay, this is what I wanted to say. Okay, so here is one question from the assignment. So you are given a contour, okay. So you don't know the exact figure now, you are just given with a contour. So there are 4 regions marked. So this is region 1, this is 2. Okay, I'll pick some different color. This is region 2, this is region 3. Okay, I need to change. This is region 3 and this is region 4. Okay. So now the question that they have asked is which region is steepest? Okay, so can you guys please answer, like, which region do you think is the steepest over here?
4, sir.
Okay, why? Why so?
Because distance from all the points is very large at 4.
Okay, so what I said over here is that if you have less gap, that means your function is more steep. So more gap would mean less steep or gentle. Okay, so like you're thinking in exactly the opposite direction. So we want to look for a region where lines are very close to each other.
3, sir.
Yes, 3 is the correct answer. Somebody typed in the chat box also. Right. So 3 is the correct answer over here. So reason 3 is correct answer. Okay. Okay. So the question, I haven't mentioned the question over here, but the question is, let's say you have this 3D plot. We want to draw the contour map for this. Okay. So we want to draw. Okay. Contour map for this. I'll wait for 1 or 2 minutes. What you guys can try is you can draw this in your notebook. Then I'll draw, and we can match whether we have got the exact same answer or not. Okay. So you guys, I'll wait till 6:22 or 6:23. You guys can try drawing, and then I'll also draw. So you just need to find the contour map for this paraboloid. So I think it is called paraboloid, something like paraboloid. Okay, let's wait for 1 more minute so that you guys can draw. Okay. So let's say if I cut my plot at this particular point where I have drawn this thing, imagine this red thing as a plane that I might not have drawn it very beautiful, but imagine that this is a plane where I want to sort of, yeah, I want to cut my plot with this plane. So what kind of figure I would obtain? I would obtain a circle over here. Okay, so I'll obtain a circle over here. Okay, so let's say the value over here is 2. Okay, the function value over here is 2. This is z is equal to 2 over here where it is cutting. Let's say if I go above this to some point which is above this. Now if I cut this thing, what values would I obtain? So I'll again get a circle, but the circle that I'll obtain would be larger than this one. Okay, larger in area than this one, right? You remember you have to compress everything to this level. Okay, so I'll get a circle like this. Okay, so let's say this is value 4. Okay, now if I cut a smaller point, let's say this is where I want to cut. Okay, so again I'll get a circle, but that circle will be now with a value lesser than this. So what I'll obtain is I'll obtain many concentric circles, and this is the sort of contour that we'll be obtaining, right? So we will have many concentric circles. So this is the contour that is obtained. I hope this is something that you drew. Okay. So we have one more question. Okay. So there are 4 figures over here, A, B, C, D, and there are 4 contours, 1, 2, 3, 4. You have to match the correct figure to their respective contours. Okay, so can you guys please like sort of answer it or type? So you have to match. For example, one is contour of what? So one would be matched to something. Okay, then 2 is contour of something. So this way you have to match the figure. I'm waiting for some answers in chat. Om Prakash has answered something. Others can also sort of try. This is not very difficult. But, yeah. Others can, like, I'm not, I haven't checked the answer, but others can also sort of write it. Just remember one thing, that the orientation can slightly change. So the figures that are here are presented in such a way that you can see the 3D image. like because this is a 2D plane that we want to show a 3D image on. So yeah, so somebody has some other answers. Okay, we'll try. So if we look at this figure, right, if we draw plane cutting, let's say at this particular, if this is my plane, so what I would obtain are just some parallel lines, right? So these lines have same value. Then here this line have same value at some particular height. So A should be matched to something looking like 4. Okay. Because we have some parallel lines, so A should be matched to 4. So both these guys, whoever have replied, they have matched 4 to A, right? That is correct. Now, if you look at B and you sort of intersect it somewhere, let's say you cut it from here. Very difficult to draw. That too, I'm very bad at it. Okay, so like if you imagine this, then if you cut this thing from here, then you will get circles, right? At the bottom, if you cut, there will be a round thing that you would be obtaining because this is curved like this. Okay, the circles might not be closed in some case, and yeah, so this is one thing. And if you look at the D and B are almost similar to each other. The only difference is D is more steep than this thing initially, and later on it has sort of flattened. But this thing is sort of at a similar kind of steepness, right? So this is one thing. So what I feel is this 2 and 3 should be matched to B and D. Which one should be mapped to what? So if you look at this one, when you are at very bottom, okay, then you are getting closed circles, but as you open up, the circles will sort of open, okay, and same is with D also. So only thing that we have to see is whether its steepness it remains constant or it is increasing and decreasing. So if you look at this case, here we can see that the steepness is sort of this is very steep at the bottom, and then it is sort of yeah, okay. So this D I think should be matched to this thing because over here the steepness is not at the bottom, so bottom circles are slightly far apart, and then B should be matched to 3. This is my opinion. But again, this is slightly confusing because we don't have a complete 3D image. So even if you have matched 2 with D and vice versa, that is correct. Okay. And the only thing that is left is 1 with C. Okay. You are saying D with 2? Yeah, that's how I have also matched. The reason that I have in mind is that like when you go very low, then the this sort of steepness is here we have sort of constant steepness. Okay. So there is one more question over here. So this is from previous year's assignment. The question is, what does the distance between two contour lines on a contour map represent? Okay. So we have discussed this quite a lot. So this is whether it is the change in output function, this is incorrect. The direction of function, this is also incorrect. The rate of change of function. So distance represents the rate of change of function. C is correct. Okay. So we are done with contours. Any doubt with contour portion?
Sir, if we are given contour map, then how can we find that which point is the down point and which point is above point in 3D image, sir? Consequent 3D image of that contour map.
See,
Can you show us
either,
reverse?
okay, so
Reverse.
I'll tell you. So either, for example, in this contour map, you are given the values over here. This is 1, this is 1.5, this is 2, right? Otherwise, it would become very difficult. So you should have either value or something like color coding like this. So for example, they have color coded if the value is high, it is more towards red. If the value is low, this is more towards -3. Otherwise, it won't be possible, because I can give you an example. Let's say you consider this was a paraboloid kind of structure. Now consider a similar structure but a downward open. Okay, you will get exactly same contours, but the only way you can find is if you have values written over here, or you have color coded your contour. Otherwise, it won't be possible, because we are mapping some 3D image to 2D image, so we are losing some information. So that information need to be represented in some other manner.
If some function is given, sir, then how to find the contour? F of xy is given with some contour, some function.
So this is what I talked about initially. So let's say if you have some function given, what you will do is you will choose some heights and you will draw some plane cutting your function at those particular heights. Okay. So for example, this you have chosen 4 heights and you will cut your plane at those particular heights. Okay. Now you will draw the points. So you will mark your points where your function was cut by these planes. So for example, they have represented this orange thing that I am drawing over here. Okay. Now next step would be to just forget about your 3D image and just remember what kind of cuttings that you obtained. Now you have to represent all these cuttings in a 2D plane, so you need to just compress this cutting. So this circle over here has been mapped to this circle over here, and this infinity thing is this infinity thing. So you just need to see them as one. This is how you will obtain the contour. I hope I was clear to whoever asked how to obtain them. Okay. Anybody else has anything to ask? Then I'll move to some. Okay, so this is something called momentum-based gradient descent. So now, let's say we'll take example of this contour that we have. Okay. Okay. So let's say you start your initial point from here. Okay, so you want to minimize your function. Okay. So let's say you started your function from here. Okay. And the direction that you're moving is sort of this direction. Just imagine right now that you want to move in this direction. If you take your step size to be sufficiently small, then from moving from a value from 2 to 1, you want to reach -2, but for just moving from 2 to -1, you will take too many steps. Okay. So this is a common problem with gradient descent, that you need to very finely tune your you have to keep updating your learning rate. Otherwise, there might be some portion where you might do very slow. Okay. So to overcome this, what people have proposed is something known as momentum-based gradient descent. So what it does is, so your update that you're making not only depends on the current gradient values, but also on the gradient values that you have obtained in the past. Okay. Now, one thing is, let's say for this example, uh, if you are constantly moving in this direction only, taking small steps, then what will happen is the gradient that you will have at previous iteration and the gradient at this iteration will have very less deviation from each other. So if you are taking the sum of both these, so in the next iteration you will move at a much farther pace, like much faster pace. Okay. So this is the idea behind momentum. So what we do is, so the update that we are making is not just the current gradient, but also some gamma times the previous update that we have made, or all the previous gradients. Okay. So if you remember, your gradient descent update was Wt plus 1 is equal to Wt minus eta times of gradient of okay, this notion is not very great, but yeah, this is L with respect to W. Okay, this is what we were doing. So now what we will do is, so just remember this gradient W2 is gradient of loss function with respect to WT. Okay, the L is sort of omitted over here. Okay. Okay. So this is something that is known as momentum based gradient descent because you are adding the previous updates also. Okay. So the advantage of this is when you have flatter surface, this is fast. Okay. And the disadvantage is because this is running very fast, sometimes you might miss your goal and then you will have to come back and so for example over here, let's say you take bigger steps, you want to, let's say, reach here. If you take your bigger steps, there is a possibility that you will reach here, then again you will have to come back, again you missed it, then again, so this kind of loops can form, which might take still might take time, but the time that it will take even after this looping process would be lesser than your normal gradient descent. Okay, this is one advantage of this thing. Okay, so there is, I think, one question on this. Okay, so this is slightly different question. So question is that we are training a neural network using normal gradient descent method. So this is your vanilla gradient descent. Okay, we observe that the change in weight is small in successive iteration. What are the possible causes for this phenomena? Okay, so what is the change in weight that you have? Wt plus 1 is equal to Wt minus eta times gradient of L at W. Okay, so if Wt plus 1 and W2T are very close to each other, what is the possibility that this value over here is very close to 0? Okay, so when would it be close to 0? So either your eta is small or the gradient value that you are getting is small. If any of this condition is true, then your updates would be very small. So there are two correct options over here: eta is small or gradient of W is small. If any of these two are true, then you will suffer. Okay. So can you look at this question and tell me what is the answer? So question is, if we start from point C, this is my point C where I want to start from. Okay. So which of them is most likely to be true? So we are starting gradient descent from point C. Where do you think would we converge?
B dash.
Yes. So B dash is somewhere we will converge, because if you see you are at a slope which is decreasing, so gradient descent would suggest you that you should move in this direction. Okay, so then you will keep coming here because this is gradient descent, you might be slow, but if you tune your lambda accordingly, you will reach B dash. So algorithm will converge to B dash. Shubham wrote it correctly in this thing. Okay. Okay. So when we did momentum based gradient descent, I discussed about one disadvantage, that because this is running very fast, it might skip the point and will have to take a lot of loops or U-turns. Okay. So to overcome this, there is something that is called as accelerated gradient descent. This is next to accelerated gradient descent. We can call it NAG in short. I'll draw a figure to tell you what is the logic behind it. Okay. So let me draw. Okay, so let's say this is your plot. Okay. Let's say you started from somewhere here, then you made some update and you reached till this point. Okay. Now, if you are using momentum based method, from here also you are being suggested to move in this direction only, and your previous iteration also suggested you to move in this direction only. So this is your x-axis, right? So x-axis has two direction. Either you can move this side or you can move this side. Okay. So your first, okay. So when you were here, you were suggested to move this much over here. Again, when you have reached here, your current gradient is also suggesting you to move rightwards, and your previous gradient is also suggesting you to move rightwards. So you will sum both of them. So the direction that you are moving in, you will sum both of them, and you will move a larger distance. Let's say you move this much, and you reach this point. Okay. Now your previous update is already big, and again your current position is telling you to move this much in this direction. So let's say from here you move till somewhere here, because you'll keep taking bigger and bigger steps because of the confidence that you are getting from your previous values. So let's say you reach somewhere here. Now what happened is you are seeing that I should have not come here. Now I'm being suggested that I should move this much. Okay. So now how much you should move again is sort of based on what is the value of gamma that you choose, because this is a weighted average between the previous thing and eta times the current thing. So let's say there is a possibility that whatever amount you are being suggested to move here is less than what your momentum term is giving if your gamma is not small, and you might still move a very small value over here and you might reach here. Okay. Now what will happen is that now you will be again suggested in this direction, and eventually you might again start moving in this direction. You might reach here, then you again might reach somewhere here and loop to reach here. Okay. Now the problem why this loopy thing is happening is when I'm here, when I'm at this particular point, one thing is whatever my previous things will suggest me, that much I'll definitely move. Okay, so let's say my previous contribution is, let's say, this much. I'll move till this point, that is for sure. And also starting from this point, I'll move whatever my gradient is suggesting. So in momentum based method, what was happening was your Wt plus 1 was Wt minus gamma times Wt minus 1. This is not Wt minus 1, but yeah, this is gamma times the update you have make till t minus 1 plus eta times so this is minus eta times the current gradient. Okay, so there are two components, and the first component is guaranteed that you will move this much. So if you can see that after moving this gamma times update, you have overshoot your the value where you wanted to reach, and the gradient is being suggested in the previous direction. So what you can do is, rather than looking at the gradient at this point, that is your Wt, you can look at the gradient at this W star. Okay. So because now W star is suggesting that you should have moved backwards, you will take sum of both of them. So what you will do is Wt plus 1 is Wt minus this gamma times update of t minus 1 plus this is gradient eta times gradient at W star. So there is a possibility that this black line would become smaller and you would reach somewhere here. Okay, then again you can sort of loop it. So looping structure will be here also, but the length of loops, so this perturbation, let's say this is your perturbation for momentum based method. So the for your this particular method, this energy method would be smaller as compared to your momentum based method. Okay, so formally this is that I have taken from lecture itself. So what you are doing is, rather than calculating your gradient at the current point, so current point is Wt, you are not calculating your gradient at Wt, but you are calculating your W at this W star or look ahead point. Okay, and then you are just doing the momentum update similar to what we have discussed. So this method is called NAG. Okay, so Nastrov accelerated gradient descent. And this has advantage that it is faster than your momentum based method because there is less of U-turn or loopiness over here. Okay. Okay, so here is a question. The question is, which step does Nesterov accelerated gradient descent perform before taking the updated size? Okay, so what does this do? So if you are at a particular point, you will first estimate your next position, that was your W star, calculate the gradient over there, and then use both these values to update. So estimating the next position is something that is a USP for your NAG method. Okay. Okay, so any doubt in this momentum based method? We have discussed two momentum based method. One is this NAG and another one is the simple momentum gradient method. Any doubt in this? Then we'll move to SGD and mini batch gradient descent. Okay. So I have discussed this thing in past, but I'll sort of revisit because this is done in this week. I was not aware that it would be done in this week. I thought it won't be done, so I discussed it before. So when you have some supervised learning setup, your data sets look something like xi comma yi, right? And let's say you have n number of training points. Okay. Then how does your gradient descent look? So your loss function would look something like summation of I is equal to 1 to n. Okay, so I can use capital L over here and small l over here. So your loss, this is the total loss, looks like loss function of f of xi comma yi. What kind of loss functions you can define? These things we have discussed in past. Okay. So this is how your loss function that looks like, and you want to minimize this L total. So how would your gradient descent look like? So W would be W minus the gradient of this particular thing. Now gradient is just taking derivatives, right? So if you have, let's say, dy by dx of f plus g, then you can split your derivative with respect to some, right? This is d by dx of f plus d by dx of g. So gradient is nothing but some combinations of partial derivative. So you can also split this for summation. Okay. So this is nothing but summation I is equal to 1 to n gradient with respect to w of L at this particular point. So you will calculate gradient at all these points, take their sum, and then update. So this is what happens in your gradient descent. Okay. Now the problem with this particular method is that let's say if you have many points, then to make even one, so if you look at this example that we talked about, just to take one step, you will have to go through all the data points, calculate their gradient, take their sum, and then you will be able to take one step. And if you sort of fall in some low steep area, so where your steepness is gentle, so then you will have to take, let's say, 1,000 steps to just cross that thing. Okay. Then going over all the points 1,000 times would become very compute heavy. Okay. So what we do is, rather than taking all these points, we do something that is known as, first I'll talk about mini batch gradient descent. So you had n points. You can split your data set from, let's say, x1, y1 to, let's say, xm, ym. Okay, right now I'm splitting it in just two sets. Okay, and next split you can have from, let's say, xm plus 1 to xn comma yn. Okay, now what I'm suggesting is, rather than summing this gradient over all the data points that you have, what you can do is, so let's say you begin with W naught, okay. So you obtain your W1 just by taking first m data points. First m, or you can choose some random m values. So you can rearrange, reshuffle and take m out of them, okay, for first m values, and then you just update it, okay, and you have obtained W1. Now starting from W1, you update it through rest of the data points that you have, okay. So start from m plus 1 to n gradient of L f of xi. Okay, so now because we are updating our weights not on the complete data set but on mini batches, that's why this variant of gradient descent is called as mini batch gradient descent. This is called mini batch gradient descent. Okay, so right now I had just 2 batches. You can have many batches, right? You can have 100 batches, 1000 batches based on whatever the nature of your data set. Or you can also fix the size of your batch. Let's say you say that I'll have 32 data points in every batches, and then I'll decide how many batches I have to make. Okay, so this is one thing that you can do. So this method is called mini batch gradient descent. So this speed up your process because now you don't have to go through all the data points just to make one update, but you can update your weights based on lesser number of data points. Okay, so there is a extreme corner case for mini batch gradient descent that is called as stochastic gradient descent. So what happens in stochastic gradient descent is, rather than now taking mini batches also, you will update your data this weight just based on one data point at a time. Okay, so what will happen is you will have W naught, then your W1 would be just W naught minus uh, eta times gradient of first point, that is L of f of x1 comma y1. Okay, and for W2 you will use your W1 minus eta times gradient of second point. So this first second point need not be in order in which your data set is available to you. You can randomly pick first point from your data set. You can randomly pick your second point from your data set, and that's the motivation behind calling it as stochastic gradient descent. Okay. Any doubt in this? What is mini batch gradient descent and what is stochastic gradient descent? Then we'll talk about some sort of properties. Okay. So again, I'll use the same figure. I think I have only one sort of contour with me. So I'll try to explain how this stochastic gradient descent or mini batch gradient descent works. So let's say, just forget about these values that are written over here, 2, 1, just forget about it. Let's say you start from here and you want to reach till this point. So I'll mark them by red. So you want to reach here and you have started from here. Okay. So what would gradient descent do is, it will just keep moving in some small steps, it will keep taking, and it will sort of reach your destination. Like, might not be in a straight line, but it will reach. Okay. What would your now stochastic gradient descent do is, it will look at the first point and it will sort of move in some direction. Okay. Let's say the first point told it that you should move here. Now second point is telling, no, you should haven't moved in that direction, you move in some other direction. So it will come here, then probably here, okay, then here, then here. Because for one epoch, you will go through all the data points. So after you have went through all the data points, so your sort of the values will lead you to the point where you want to reach, but there would be a lot of randomness in the work that you are saying. So there would be a lot of this kind of nature in the work, and mini batch gradient descent would lie somewhere between them. So there would be less of randomness but there would be randomness because you are not taking all the data points at. Okay. Again, any doubt in this gradient descent, mini batch gradient descent, stochastic gradient descent? One more thing, like the way you merge gradient descent with momentum based gradient descent, or you merge with energy, you can still merge your mini batch gradient descent or stochastic gradient descent with both these things. You can merge them with momentum based method and energy based method. Those are also possible. Okay. Okay, so if nobody has doubt, nobody is saying. So we'll move to the questions. Okay, so the question is, which of the following algorithm will result in more oscillation of parameters during the training process of neural network? Okay, the options are stochastic gradient, mini batch gradient, and batch energy. So batch, yeah, somebody has something to say. Okay.
Stochastic gradient descent, sir.
Stochastic is correct answer. What I wanted to say is this batch gradient descent means that you are using all your data point at once. So this vanilla gradient descent is also called as batch gradient descent. Okay. So there can be some confusion between whether batch energy uses has more sort of perturbation or the stochastic gradient descent have more perturbation. So stochastic gradient descent will have much more oscillation because when you look at energy, let's say you want to reach this point and you have started from here. Initially, it will move right, but when it will overshoot, then only it will take some U-turn and those kind of things. This is the structure of energy. But when you talk about gradient descent, from beginning only it will start taking some random steps. It might go here, then come here, then come here. So there will be much more oscillations in gradient descent, this stochastic gradient. Okay. Okay, so select the parameter of vanilla gradient descent. I think there should be a that over here that controls the step size in the direction of gradient descent. So what controls the step size? What do we call the parameter eta?
Learning rates.
This is called the learning rate. Correct. Okay. So the question are, what are the advantages of using stochastic gradient descent method instead of vanilla gradient descent? Okay. So first option that is given that we are theoretically guaranteed the descent direction in the optimal direction in SGD. So we don't have any such guarantees because we will have only one point at a time. So one point would modify the gradient based on its will, and it doesn't care about all the rest points. So this option is not correct. SGD oscillates less compared to vanilla gradient descent. This is again incorrect. Vanilla gradient descent is the one which would oscillate minimum, right? So SGD oscillates a lot. So this is also incorrect. SGD converges faster than vanilla gradient descent. This is correct, right? The weight update is tiny at a gentle loss surface for given gradient descent. So I didn't understood your question, Vinu Murugan. So what is the question? Yeah, so weight update is tiny at gentle loss surface when you're using gradient descent. The statement is correct, like whatever you have written. Because when you have a gentle surface, the gradient values that you get are very small. Okay, so let's say I'll just if I got your question correct, it is you are asking whether this statement is correct or not. Let's say I have this curve and I have this curve. Okay, this is gentle surface. So you tell me which one has higher derivative at, let's say, this point or points in this range. Okay, because this is flatter or gentle, this has lesser derivatives. So value of derivative is less over here. Yeah, these lectures are getting recorded. That's why the gradient values that you get on flatter surface are small. Now, because your gradient are small and your, let's say you have chosen your eta even to be, let's say 0.001. So the updates that you would be making in W would be small. So that's why you, yeah, the weight update is tiny in case of gentle loss surfaces for gradient descent. So SGD converges faster than vanilla gradient descent. This is correct, because the reason that I just discussed, gradient descent will converge very slowly for your sort of this gentle loss surfaces. SGD is computationally efficient for larger data set. This is also correct, because you have to calculate only one gradient for one update. Okay. In case of gradient descent, you have to calculate gradient at all the points just to make one update. So this is computationally more efficient. Okay. So any doubt till this point, so that we can talk about something called line search? Any doubt? Okay. So this is something known as line search. Okay. So right now, whatever we have seen gradient descent, we have seen momentum based method, NAG, stochastic gradient descent, mini bias gradient descent. All of these were dependent on a factor called eta. So eta is your learning rate. Now the question is, how do you decide on eta? So like if you look at the lecture, there are two or three very good options given. One is that you begin with, let's say, 0.1. After doing certain iterations, you divide it by half. Let's say after 5 or 10 iteration, you use 0.05. After 10 iteration, you again divide it by half. So on you can approach. This is one method. Second method that professor suggested was like, let's say you pick 0.1 and you keep using this learning rate till the time your loss is decreasing. Okay. Whenever you encounter that your loss has increased from your previous iteration, go back to the last iteration and update your this learning rate to, let's say, divided by 10 or divided by 2. Okay. So this way you can get the optimal learning rate. Okay. So these are the two methods that were discussed over there. One more method that was discussed is known as line search. What you do is you fix a set of etas that you want to pick from. Okay, so let's say you have made a set having 10, 1, 0.1, 0.001. Okay, let's say you have created a set something like this. Okay, now I'll talk it in context of gradient descent, but you can apply it for every method that we have discussed so far. Okay, so what you will do is, when you have calculated your gradient, let's say you calculated your gradient, you will, so let's say this is your loss function. So this is, let's say, 1, 2, 3, 4, 5, 6 values are there. Okay, what you will do is you will calculate all the 6 W's. Okay, so what you will do is you will have W1, which is let's say this was your initial W minus 10 times gradient. Okay, this is one thing that you will do. You will calculate a W2, which is W minus 1 times of gradient of W1. And so on, you will calculate till W6. Now what you will do is, you will evaluate your loss function at all these W's. Okay. And at whichever W you got your least loss, you will pick that particular W or the value of eta that you have. Okay. This method is something known as line search method for your gradient descent algorithm. And this way, on every step, you are guaranteed that you are picking the correct eta. Okay, but remember that you are picking the correct eta only from the set that you have chosen before. There can be eta outside the set which is even better than what you have chosen right now. Okay, somebody has raised her hand. Shashikala, you have some doubt, or it was raised by mistake? Okay, I'll continue then. Okay, here is a question. Okay, so before going to the question, I'll probably explain it over here only. Okay, so let's say the value of eta. Okay, what do you expect this value of eta when you are just beginning from some random point? Let's say you initialize your w. What should be the initial values of a lambda that you should get? So when you are starting from absolutely random points, okay, then there is a very high possibility. I'm not telling you that whatever I'm saying is 100% accurate for all the data sets that you'll encounter or all the loss function that you'll encounter. But in general, in practice, what would happen is when you begin from some random point, the optimal point would be generally far away from this point. Okay. So the initial updates that you should be making should be of larger length. Okay, and then you should keep on making your steps smaller so that you converge better. Okay, so if you do something like line search, so your initial eta should be large. Okay, these should be large. So it can be 10 or 1 or something like that. Okay, and your later ones should become small. Now there is another possibility, like let's say you are at some initial eta, so you are at initial stage and your eta is very small that you have got. So when can this thing happen? The question is, when can this thing happen? So what I'm saying is that you just started and you are getting very small eta using line search. When is this possible? What I say is, there are two possibilities. One thing is that I said the initial point is very far away from this. One possibility is that now your initial guess that you made, by some luck or by something, it was very close to the actual point where you wanted to reach. Okay. Second possibility is, now if you remember, the update that you are making is some eta times gradient of w. If you have got your gradient to be very high, very large value of gradient you have obtained, then your eta would be automatically very less because you want this your product to be large and you don't want it to even to be very large enough. Okay, so if in some case you are getting your eta to be very small, one possibility is that your gradient of w is large. Okay, this is one thing. And so yeah, there is a question related to this. I think now you should guys can answer this question. The question is that you are using line search with following eta values 0.1, 1, 0.5 again. Yeah, so at nth iteration, so one thing I can tell you is that over here assumption is n is large. Okay, so at some large iteration the eta value getting selected was 10. What can you infer about value of gradient at that point? I would like you guys to answer based on whatever we discussed a few moments ago. So I said for initial iteration, if your eta is small, that means your gradient is large. Now this is exactly the opposite case. So at later iteration, you generally want that your eta should be small, but you are getting your eta to be large. Okay. So what is the possibility? Why did your eta become large?
Gradients sir must be small then.
Yeah. So the your gradients were small. That's why just to make those things sort of constant, your eta had to be large. So your gradient is small. Okay. Yeah. This is correct. Okay. Okay. So yeah. So till now, what we have done is we discussed about two methods that were related to momentum. So first was the normal momentum based gradient descent. What was the use of these kind of methods? So use of these kind of methods was when we have gentle loss surface or a sort of flat loss surface, then gradient descent takes a lot of time. Okay. To overcome that, we had two momentum-based method. One was this momentum-based gradient descent. Another one was NAG. Okay. Then we talked about two methods, stochastic gradient descent and mini batch gradient descent. They solved a different kind of a problem. The problem that they were solving was, because if we go over all the data points just to make one update, then it will be computationally very expensive and it will take a lot of time. So to overcome these two problems, we had stochastic gradient descent and mini batch gradient descent. Okay. Then all these methods used eta. Okay. So how to choose eta? Now, one way that has been proposed is your via line search, and some other methods also I talked, and some have been discussed by professor also in the lecture. Okay. So now what happens is, let's say you have some data set where this is of form x comma y. X has some features x1, x2, xn. Okay. Now there is a possibility that there is some feature, let's say this feature is a 0 1 kind of feature, it will have value 0 or 1. There is some feature, let's say x2, which have most of the values as 0. Okay, let's say there is some feature like this. Now if you remember, when you calculate gradient of let's say this x2 is connected to next layer via weight w2. When you calculate the gradient of loss function with respect to w2, there is a term x2 that gets multiplied with other terms. Okay, so this is, if you even if you don't remember, just trust me. When you calculate the gradient of the loss function, there is this term x2 getting multiplied with some other terms. Okay. Now, because your x2 is 0 for many cases, that would mean the gradient value. So your gradient is a complete vector. So there is a component that would correspond to its derivative with respect to w2, loss function's derivative with respect to w2. So that value is 0 for many examples. This is what I'm saying. Okay. Okay. Now if you would have used gradient descent, okay, then what would happen is, so you will take sum over all the data points, I is equal to 1 to n. So if you have some non-zero values over here, still you would have updated your W2 a little bit, but the update would be small as compared to other weights. Let's say this W1 or Wn. The update would be small because the summation value would still be lesser as compared to the other summations that we are getting. Now the other case is, let's say you are using stochastic gradient descent. There you are looking at one point out at a time and you are making updates. Then you will have many cases where there is no update for W2 at all. Okay. So to overcome this problem, there is something that has been proposed called ADA-grad. So this is adaptive sort of gradient descent. So what ADA-grad does is, so initially it will be similar to gradient descent for all, but as you continue in your iterations or epoch, what would it do is, so if you have a feature which is sparse means that you have lot of zeros, then it will give preference to update of that particular weight, and it will hinder update of other weights. Okay, so if some weight is getting updated many times, then it will hinder the update of those kind of weight, and it will allow those weights to update which belongs to sparse features. Okay, so how to do that is, so we define a VT. So if you see VT would sort of accumulate all the updates that you have made. Okay, so this gradient of WT is a vector, right? So it will sort of accumulate all the updates that you have made. So if you have made large update, then it will divide. So okay, so this is your VT. Now your update is given by WT minus eta times, this is just your normal stochastic gradient descent, and there is an extra term that is under root of Vt plus epsilon, right? So this epsilon has been chosen because there is a possibility that your Vt is 0 initially for some features. Then what would happen is you will have under root of 0 in the denominator. That would not make any sense. That's why we have chosen some epsilon, that this would be very small value. Okay, so this is just, if you just ignore the epsilon for the time being, you are just dividing it by under root of Vt, where Vt is sum of all the updates that you have made. So for the features where you have made more updates, so there would be lesser update on the later part of your training, and for the features where you have made less updates initially, those features would get updated with a larger step later on. So this is how your ADA grad works. Okay, and this is the motivation behind this particular formula. Okay, so yeah, somebody
Sir,
has something to say. Yeah.
sir,
I'm listening.
regarding epsilon, if you are going to increase the iteration, in that case, epsilon is constant, or the value of the epsilon will differ from the initial value.
No, epsilon will always remain constant. Okay, we are just including epsilon so that we don't encounter a situation where we are dividing it by 0.
Okay, sir. Okay. Okay,
So
thank you.
epsilon
Thank
is some very small value that we have initially chosen, and we'll just maintain that.
you. Okay, sir. Thank you.
Okay. Okay, here is a question. Which of the following are the disadvantages of ADA grad? So I haven't discussed like what the advantage or disadvantage, but let's see what can be a disadvantage of this ADA grad matrix. Okay, so I should rather discuss before going to that question. Okay, now one disadvantage that this thing happens is, so let's say if you are, let's say, using stochastic gradient descent or even gradient descent, when you have gone past one or two epochs, okay, what would happen is this Vt value would get very large. So eventually your Vt would become very large. Okay, so 1 by under root of Vt becomes very, very small. So after some iteration, what would this ADA grad do is, because this value becomes very small, so what we wanted is, like for the features whose weights are regularly updated, we wanted them to update by small value, but what it actually is doing, that eventually it will stop it from upgrading itself. Okay, so what will it do is, it will push this value to be very, very small, and you will see very negligible update in your weight. Okay, so this is one disadvantage that it has. So this is the disadvantage it is talking about. So weight updates are very small at the, okay, so this is not, so it doesn't work well for sparse matrix. Actually, it works well with sparse matrix. So this is incorrect. It usually go past the local minima. No, this is not a problem associated with it. So the problem is it gets stuck before reaching the minima. So even when it has not reached the minima, your weight updates become very small and it gets stuck even before reaching the minima. Okay. So professor has very good illustration on this, like he has drawn many steps, you can see. So, okay. So to overcome this, what people do is they have proposed something known as RMS prop. So RMS prop is nothing. So earlier what you were doing is you were taking sums of your Vt minus 1. So you were taking Vt minus 1 and then you were having gradient square. So this square is over here so that you don't care about plus and minus value. So what we want is, we want to sort of count the number of updates and multiply it by the amount of update. So we are not interested in the sign, that's why we have squared it. Okay, so yeah, so earlier one was this thing, right? Now what we are doing is, we are sort of discounting this thing. So what is meant by discounting? Earlier we were just adding whatever we had obtained previously. So let's say you have values 1, 1, 1, 1, 4 times that you obtain. If you just keep summing, you will get 1, 2, 3, 4. This is the value. So this is your t is equal to 1, t is equal to 2, t is equal to 3, t is equal to 4. Now let's say what you do is you adapt another method of summing up. What you do is, initially you do 1, okay, then whatever previous values you have, you multiply the previous value by some beta, okay, so beta by vt minus 1, and then you sum the current vt. Okay, let's say I take my beta to be 0.5, then it will be 0.5 times the value that I have already obtained plus 1, so it would be 1.5. Again 0.5 times, so this is 0.75 plus 1, so this is 1.75. Again I'll divide it by 2, so I'll obtain something, let's say around, I'm not very sure, this would be 8 something or 9 something. So but one thing that I'm saying is, if you discount the sum, so whatever sum you have obtained in the previous iteration, if you multiply it by some value between 0 to 1 and then add that particular value to your current string, then the values that you will obtain won't shoot up very fast. Okay, so if you see just this example, when we had 1 1 1 1, the sum was shooting up to 4 in just 4 iterations. But now if you have discounted this thing, the value is remaining sort of close to 2 after 4 iterations, right? So this is the uh, like motivation behind this RMS prop. Rather than taking the direct like straight away the sum, it will multiply it with some beta, where your beta would belong to definitely 0 to 1. Okay, and for other part also it has sort of weighed it down. So this beta you have to choose carefully, or you have to tune this hyperparameter based on your validation set, and then you make similar updates. Okay, so this is same to AdaGrad, but because I don't want my VT to be very large, I just scale it a bit down while summing it up. Okay, so this AdaGrad and RMS prop, these methods were related to your gradients, how you can update your gradients. Now we learned about momentums too. So there is this method proposed, something known as ADAM. So what people have done is they have mixed both these things. They have mixed momentum as well as your I think there is one thing missing over here. Okay, I'll write. So they have mixed momentum as well as your RMS prop to obtain something known as ADAM. So I'll just write, I think I'll write this correctly, Wt minus some eta times. Okay, and rather than having gradient, we will have momentum now, and rather and this Vt will remain same. So Vt, I think I'm correct. I'll just verify this one so that I don't write this thing incorrectly. Just give me a second. I think I am correct, but I'll just verify. Yeah, this is correct. Okay. Okay, so this is cap over here, the had that they have defined just to uh, keep the expectation same. Those things you can check over there in the code. So this is the idea behind it. Now, all the problems that your gradient descent method suffered, okay, the problems that it suffered was that it was slow, right? For that you proposed momentum. Okay, now if you see, we talked a disadvantage of AdaGrad, that it generally stops before this thing, so that means it has become very slow over there. Okay, now if you mix it with momentum, then there is a possibility that it won't die over there and it will converge to the point that we wanted to converge. Okay, so this is the motivation behind your ADAM optimizer, and this is one of the most common optimizer still that is being used by deep learning community. Okay, so you just need to, the way you were taking the weighted average or the moving average of your gradients, you need to do it with your momentum now, and the second term is just same. and rather than updating based on gradient, you are updating based on this momentum. Okay. Okay, so in the last year's assignment, I didn't found the questions on RMS prop and Adam, so it's not here. But if you have any doubt related to this, I'll be happy to answer. So I didn't had a lot prepared today. Again, I'll stop the recording and then I can